So if you recall from the last video where we had done this air standard Otto cycle, if you remember this cycle, this has two isentropic processes, which are 1 to 2 and then 3 to 4, and then two constant volume processes, 4 to 1 and then 2 to 3. When we go to the next cycle, keep that in mind. So now if you look at the air standard diesel cycle, the difference is the step 2 to 3 where we supply the energy, instead of being a constant volume process, now it has become a constant pressure process. Other than that, the whole process is the same. So you have 1 to 2, which is isentropic compression, then 2 to 3, which is the constant pressure heat transfer, and it's also part of the power stroke. Then 3 to 4 is an isentropic expansion, which is the power stroke, and then 4 to 1 is the process where we reject heat at constant volume. So this is a PV diagram, and you can also do the same thing on TS diagram. The difference, of course, would be here that the isentropic process are these vertical lines, because the entropy remains constant along this line and along that line, and then constant pressure, and then this is a constant volume process. So let's analyze this cycle. So again, remember 4 to 1 is a constant volume process, so the work done would be 0. 1 to 2 and then 3 to 4, they are isentropic process. That means they are also adiabatic, and therefore there won't be any heat transfer. And we are assuming that this is a closed system, because we are saying that, okay, in this internal combustion engine, the same air is being circulated. So we can call that to be a closed system rather than a controlled volume, because there is no mass or material transfer. And we can safely assume there is no change in kinetic energy and potential energy. So in that case, the work done during this process 2 to 3 would be just pressure times the change in volume, because pressure is constant. And then using the first law of thermodynamics, which would give us how much is the Q23, how much is the energy transferred during this process, would be change in internal energy plus the work done, which is P times change in volume. Now, if you go back and look at the overall energy balance, that would give us basically Q23 as change in enthalpy, because U3 plus P times V3 would be the enthalpy at state 3, and U2 plus P times V would be the enthalpy at 2. So this can be simplified to this. And during 4-1, since there is no work done, then the energy transfer or the heat transfer or the heat rejected in this case would be just the difference of internal energy, because there is no work done. And so from there we can see what the efficiency would be, which would be W cycle divided by the heat input, and that's given in terms of the change in internal energy and change in enthalpy. Now, since we are looking at these, whether it's a diesel cycle or an Otto cycle, or the next one that we are going to do, Brayton cycle, in many of these cases only the compression ratio is given, which means it tells us by what factor does the volume change, and we may not really know the actual volumes. So this is the place where we can use the information that's given in tables A22 and A22E, where you have the value of relative volumes. So remember, it's the same thing in Otto cycle. We have these relative volumes, and you need to make sure that you don't confuse that with the reduced volume, because reduced volume is different than relative volume. And these relative volumes and relative pressures are actually listed at each temperature for air as an ideal gas in these two tables. And the property of these relative volumes is that the ratio of relative volume is the same as the ratio of the actual volume, or the ratio of VR2 or VR1 would be same as V2 or V1, or VR2 relative volume at state 2 would be relative volume at state 1 divided by R being the compression ratio. Also, you remember that since we are dealing with ideal gas, and since pressure is constant during this process 2-3, that means from ideal gas law, PV equal to nRT, we can calculate the relationship between the temperature of at these 2 points, 0.2 and 0.3, in terms of this cutoff ratio, which is the volume of 3 divided by volume of 2. And then again VR4 in terms of VR3 given these two quantities. So the idea is we only need to know these, in this case we only need to know this R and RC, the cutoff ratios, rather than the actual volumes. So once we have this information, which relates basically volumes to relative volumes and then temperature to the temperature at two places in terms of this RC, we can go back and do an analysis for the cold air standard analysis, where basically the heat capacities are constant. So in that case, if heat capacities are constant, our change in internal energy would be Cv delta T, and change in enthalpy would be Cp delta T. And so I'm using these relationships just for the polytropic process. So if you go back and look at this, polytropic process means this 1, 2 and process 3, 4. You can use those earlier relationships to find temperature ratios in terms of the compression ratio, and similarly T4 over T3 in terms of RC over R. And of course this is one that we saw earlier. So combining these three relationships along with these two, if you go and plug them in here, so replace delta U4 minus U1 by Cv times T4 minus T1, H3 minus H2 by Cp times T3 minus T2, and then eliminate the temperatures using these three equations. Then we get a efficiency which is given only in terms of R, which is the compression ratio, RC, which is the cutoff ratio, and this K, which is the ratio of heat capacity for the ideal gas. So it's a relation, so it does not require you to know volume as such. We can still calculate the efficiency by just knowing these quantities. And if you plot this now, thermal efficiency versus compression ratio, as RC being a parameter, then first of all you notice that as the compression ratio increases, the efficiency increases. But as RC increases, efficiency decreases. So basically what we are saying that the first situation, the Otto cycle, when we had RC equal to 1, basically gave us the best result. And then if you make this, instead of a vertical line, if you change it to a horizontal line, which is a constant pressure process, then efficiency would be somewhat reduced.